Welcome back, everyone, to our ongoing deep dive into the OOIS, the Online Encyclopedia of Integer Sequences.
Okay.
As always, it's a pleasure to have you with us.
Yeah, great to be here.
As you know, it's this vast and fascinating collection of integer sequences, and we're uncovering hidden gems with each episode.
Absolutely.
So today we're going to be focusing on sequence A000141,
Okay.
which delves into the world of representing numbers as the sum of 6 squares.
All right, cool.
Sounds interesting.
This is a fun one.
Yeah, this sequence might seem simple at first glance, but as we'll discover, it has deep connections to various branches of number theory.
Right, and the sequence itself starts like this: 1, 12, 60, 160, 252,
Okay.
and so on.
Wow.
I'm already intrigued.
Yeah.
What do these numbers actually signify?
So each number in the sequence represents the number of ways you can express a given whole number as the sum of 6 squares.
Okay.
Let's take the first few numbers as an example.
Yeah.
For 1, there's only one way, right?
1 squared plus 0 squared plus 0 squared plus 0 squared plus 0 squared.
Makes sense.
But for 2 things get interesting.
Okay.
We have 12 different combinations.
12. That's quite a jump.
Yeah.
What causes this sudden increase in possibilities?
It's what we call combinatorial explosion.
Oh, okay.
Think of it like this.
Right.
Imagine you have 6 slots to fill, each representing a square.
Okay.
As the number you're trying to represent gets bigger, you have more options to choose from for each slot.
Okay.
This leads to a rapid increase in the number of possible combinations.
That makes sense.
Right.
Now,
Yeah.
looking at the OEIS entry, we see a formula
Okay.
attributed to Jacobi.
Right.
Can you help break this down for our number theory students?
Absolutely. The formula might seem daunting at first glance, but let's dissect it piece by piece.
Perfect. Let's dive in.
All right. So the formula relies on a few key concepts,
Okay.
namely divisors and modular arithmetic.
Okay.
Let's start with divisors. A divisor of a number divides evenly into that number.
Right.
For instance, the divisors of 6 are 1, 2, 3, and 6.
Okay, so the formula considers all the divisors of the number we're working with.
Exactly.
What role does modular arithmetic play in this?
So modular arithmetic deals with remainders.
Okay.
You'll see terms like d congruent to 1 modulo 4 in the formula.
Right.
This simply means that when the divisor d is divided by 4,
Okay.
it leaves a remainder of 1.
So the formula sifts through divisors based on their remainders when divided by 4.
Yes.
I'm beginning to see how this all comes together.
Yeah, it's pretty neat.
Jacobi's formula ingeniously combines these concepts to count the ways we can represent a number as a sum of 6 squares.
Exactly.
It's impressive how elegantly the formula weaves these concepts together.
It really is.
But there's another element in the OEIS entry that caught my eye.
Oh.
Theta functions.
Okay.
What are they and how do they connect to our sum of squares sequence?
Theta functions are a fascinating area of study in number theory and analysis.
Right.
They have this unique property where their coefficients can encode sequences like ours.
Oh.
Specifically, if we take a particular theta function and cube it,
Uh-huh.
the coefficients in the resulting power series will correspond to the terms in our sequence A000141.
So theta functions offer a way to represent the entire sequence in a compact form.
Precisely, this connection demonstrates a profound link between number theory and analysis, showcasing how seemingly different areas of mathematics can intertwine beautifully.
Yeah, it's really cool.
It is fascinating. Yeah, it really is a testament to the power of these special functions to encode complex number theoretic information.
I'm starting to see how even a sequence as seemingly simple as this can lead to profound mathematical connections.
Absolutely.
The OEIS entry also mentions a generating function identity
Right.
by Wolf-Dieter Lang in the comments section. What can you tell us about it?
So generating functions, as we've touched upon, are powerful tools for representing sequences.
Right.
This particular identity provides an alternative way to express the generating function for our sequence.
Okay.
What makes it intriguing is that it involves infinite series with terms that incorporate familiar number theoretic concepts like squares and alternating signs.
So this identity offers another perspective on the sequence, linking it to the world of infinite series.
Exactly. Each representation of the generating function illuminates different facets of the sequence and its connections to various mathematical areas.
Okay.
In this case, it ties our sequence to concepts in analysis and the theory of modular forms.
It's incredible how one sequence can act as a bridge between so many diverse areas of mathematics.
Yeah, it's really fascinating.
Now we focused on sums of 6 squares.
Right.
But the OEIS entry also hints at connections to broader formulas for sums of squares. Can you elaborate on this?
Absolutely. There's a rich history of studying how numbers can be represented as sums of squares.
Okay.
A famous theorem, for instance, states that Any positive integer can be expressed as the sum of four squares. Our sequence A000141, focusing on sums of six squares, falls within this broader landscape.
I see. So are there similar formulas for representing numbers as sums of different numbers of squares?
Yes, there are formulas for sums of 2, 4, 8 squares, and so on.
Wow.
Each formula has its own unique structure and reveals intriguing patterns within the world of numbers.
Okay.
What we've been exploring with A000141 is a specific case within this broader family of formulas.
It's like we've zoomed in on one particular branch of a vast and interconnected mathematical tree.
That's a great analogy, and the OEIS is like a map that guides us through this intricate forest of mathematical connections.
Speaking of connections, the OEIS entries also has a cross-ref section that links to related sequences.
Right.
What insights can we gain from exploring these links?
The cross-ref section acts as a roadmap pointing us towards other OEIS entries that share connections with our sequence. For example, it mentions sequences related to sums of divisors with specific congruence conditions.
Okay.
These connections hint at underlying relationships between different number-theoretic concepts.
So these links offer a way to delve deeper into the interconnected web of number sequences.
Precisely. It's like a treasure hunt, where each discovery leads to more exciting paths to explore.
This is truly fascinating. It's amazing how much depth we've uncovered by starting with a seemingly simple question. How many ways can we represent a number as the sum of six squares?
It's a testament to the beauty and richness of mathematics.
Yeah.
Even seemingly elementary questions can lead to profound insights and unexpected connections.
Before we wrap up our exploration of A000141, I'd like to take a moment to recap what we've learned.
Sure.
We started by understanding what the sequence represents. The number of ways to write a whole number as the sum of six squares.
Right.
We then delved into Jacobi's formula, which ingeniously uses divisors and modular arithmetic to calculate those numbers.
Right, exactly.
We also discovered the surprising connection to theta functions, highlighting the fascinating interplay between number theory and analysis. And we saw how A000141 fits into a larger family of formulas for sums of squares, expanding our understanding of this fascinating branch of number theory.
Yeah, it's amazing how much we've covered.
It's been an incredible journey through the world of A000141, but before we conclude, I'd like to touch on one more aspect that often adds a layer of richness to our understanding of mathematical concepts: the historical context.
That's a great point. This sequence has a long and intriguing history with connections to some of the greatest mathematicians of all time.
Indeed. Can you share some insights into the historical development of this sequence and its related concepts?
Of course, the problem of representing numbers as sums of squares has fascinated mathematicians for centuries.
Right.
One of the early pioneers in this area was Pierre de Fermat, who in the 17th century made a remarkable conjecture.
Okay.
He stated that every prime number that leaves a remainder of 1 when divided by 4 can be expressed as the sum of two squares.
Interesting.
While Fermat didn't provide a proof, his conjecture sparked a wave of research.
So even back then, mathematicians were captivated by the patterns and properties of squares.
Absolutely, and about a century later, Joseph-Louis Lagrange built upon Fermat's work and provided a rigorous proof of his conjecture.
Wow.
This achievement was a major milestone in number theory, paving the way for further explorations into the world of sums of squares.
And what about Jacobi? How does his work fit into this historical narrative?
Carl Gustav Jacobi in the 19th century made groundbreaking contributions to the theory of theta functions.
Okay.
He was able to connect these functions to the problem of representing numbers as sums of squares. Jacobi derived a general formula for expressing numbers as sums of an even number of squares, which of course includes the formula for our sequence, A000141.
So Jacobi's work brought together many different strands of mathematical research, culminating in a deep understanding of this sequence and its connections to other concepts.
That's an excellent summary. His work demonstrates the power of mathematical abstraction and the beauty of discovering unexpected links between seemingly disparate areas of study.
This historical perspective adds a whole new dimension to our appreciation of A000141. It's a reminder that mathematics is not just a static collection of formulas and theorems, but a living, evolving field shaped by the contributions of countless brilliant minds throughout history.
Indeed, and the OEIS, with its vast collection of sequences and their accompanying information, serves as a testament to this ever-evolving mathematical landscape.
Wow, it's been a fascinating journey exploring A000141.
Yeah, it really has.
We've delved into its meaning, its formula,
Right.
its connections to theta functions and broader sums of squares formulas.
Yep.
and even its rich historical context.
It's amazing, isn't it?
Really is.
And what's remarkable is that this is just one sequence.
Right.
Out of hundreds of thousands in the OEIS,
Yeah.
each one has its own story to tell its own secrets to reveal.
It's like we've glimpsed into a vast and interconnected universe of numerical patterns.
Exactly, and the OEIS provides us with the tools to navigate this universe, to explore these patterns, and to discover new connections.
I'm curious for our number theory students listening in.
Yeah.
What would you say is the most significant takeaway from our deep dive into A000141?
I think it's the reminder that even seemingly simple mathematical ideas can lead to profound insights and unexpected connections.
Oh.
This sequence at its core is about counting ways to represent a number as a sum of squares.
Right.
But look where it's led us to: divisors, modular arithmetic, theta functions, generating functions, historical breakthroughs, and a glimpse into a vast family of related formulas.
Yeah, it's a testament to the power of curiosity and exploration in mathematics.
Absolutely.
Sometimes the most unexpected paths lead to the most rewarding discoveries.
Couldn't agree more. And the OEIS is a fantastic resource for anyone who wants to embark on these mathematical adventures.
Well said. This has been an illuminating deep dive into OEIS sequence A000141.
It has.
We've uncovered its mathematical secrets, traced its historical roots, and hopefully sparked a sense of wonder and curiosity in our listeners.
I hope so too.
So until next time, keep exploring the OEIS and never stop asking questions.
Great advice.
Who knows what mathematical treasures you might find?